Morning, sir.
Good morning. So, are there any questions, doubts you have? Okay, then let me start. So, last class I was discussing this eight-noded solid element. So, I had in this what we are saying is basically that all the three displays there are all the three displacements along xyz directions non-zero, and they are functions of all the three coordinates. It's not writing, so let me focus on it. Hello, is my screen visible? Okay. So last class I was discussing eight noded isoparametric brick element. So I will continue with that. So we had discussed that there are three displacements which are functions of all the three coordinates, that is uv and w, functions of x, y and z. There are known functions of x, y and z, and that is why we need a 3D modeling and 3D interpolation. So as far as strains are concerned, there are all the six components of strains are non-zero and independent, and similarly there are six components of stresses. And then we had discussed about the constitutive relation for linear elastic isotropic solid, and then the total potential energy functional. So finally, if you recall, I had written the total potential energy functional. So total potential energy functional I we had written as half, and then integration over volume, and it is actually sigma transpose into epsilon. So the strain energy is basically for linear elastic solid is half of integration over volume, and then sigma xx into epsilon xx plus sigma yy into epsilon yy, so on all the combinations. So that can be written as sigma transpose into epsilon and then sigma c into epsilon. So we can write that as sigma transpose into c transpose is equal to c. So we write it as c epsilon dv. So this is the strain energy part, and then minus we have the potential of body forces which are acting throughout the volume. So UVW transpose and the body force per unit length along x, y, per unit volume along x, y and z. So this is integral dv. And then we had the surface traction, so the integration over surface, and again the potential of those surface tractions is UVW transpose, and then you have TNX, TNY and TNZ, a force point area on a surface having boundary surface having normal along direction n ds. So I had said that this is surface area. So this was the total potential energy functional we had written in the last class, so in which is consisting of strain energy and the potential of body forces and the potential of tractions acting on the bounding surfaces. And then what we said is that we are talking of an element here. So In the physical coordinate space, if you look at the element could be arbitrary parallelepiped. So it need not be a basically a cube or a cuboid, but it can be arbitrary parallelepiped. And then the coordinate system I had taken as this as basically x, this as y, and this as z. The node numbering was 1, 2, first the bottom nodes 3, 4, and then the top nodes. So 5, 6, 7, and 8. So this is the element in the physical coordinate space, and this element is mapped. So it is transformed to the cube in the natural coordinate space. So cube in the natural coordinate space is this is the cube in the natural coordinate space, and again these are the nodes. So 1, 2, 3, 4, and 5, 6, 7, and 8. So there is 1-to-1 correspondence between the nodes 1, 2, 3, 4, 5, 6, 7, 8 in the physical coordinate space, that is xy. The coordinates are the origin is at the center of this cube here. So this is eta, and from this point on this surface you have uh, xi, and then from this surface you have this side zeta. So these are the coordinate axes, and I had written the last class I had written the interpolation function, so I'm not repeating that again. So we had written 8 interpolation functions, and then I had said that the when you look at the approximation, so within each element we are assuming an approximate solution in terms of xi and eta, and ultimately writing them in terms of shape functions. So we had u equal to summation ni u I e, v equal to summation is from I going from 1 to 8. So ni v I e, and w was summation ni w I e. So the summation is 1 to 8. So these are all the displacements UVW. They are expressed in terms of xi, eta, and zeta through the shape functions n1, n2, n3, n4, n5, n6, n7, and n8. And similarly, the coordinates x is written as summation ni xi, y is written as summation ni yi, and z is written as summation ni zi. So this is what we last class we actually did up to here, after writing the shape functions. So now if you look at we need to write the interpolation for all the three displacements together. So that is, we need to define the interpolation matrix similar to what we have been doing in other elements. So the same thing we'll have to do over here. So if you look at the displacements, so we have three displacements UV and W, and these are written in terms of the shape functions. So if you look at the shape, so this is going to be shape function matrix, and here you have the degrees of freedom. So now at each node, so when you are talking of 3D solid element, then as you see there are 3 degrees of freedom per node. And those degrees of freedom are basically displacements along three orthogonal coordinate directions x, y, and z. So for the each node we have 3 degrees of freedom, and since this is an 8 noded element, so for the element as a whole we will have 24 degrees of freedom. And those degrees of freedom are u1e, first for the first node v1e and w1e, then second node u2e, v2e, w2e, and like that you have to go up to 8. So finally we'll have u8e, v8e, and w8e. So this is the vector of elemental degrees of freedom. So this is a vector of basically as you see 24 by 1, because there are 24 elemental degrees of freedom. So this is a vector of 24 by 1. There are 24 elemental degrees of freedom, and at each node there are 3 degrees of freedom. So if you write, no, look at U is written as N1 U1 plus N2 U2 plus N3 U3 and so on. So we write here N1, and then we'll have to write the coefficient of V1E and W1E as 0 0, and then some coefficient of U2 is N2, and again 0 0, N3 0 0, N4 0 0, and like that you will have at the end N8 0 0. So these are the interpolations for a view, and then we will have same interpolation for V. So V will have 0, and then N1 0 0 because it has to go with V. So N2 0 0, N3 0 0, N4 0, and then 0, N8 0. Then W will be third degree of freedom. So we will have in the third, sixth, and ninth column and so on. So we will have 0 0 N1, 0 0 N2, 0 0 N3, 0 0 N4, and in between all the values 0 0 N8. So this is the interpolation matrix. So as you see, this is a 3 by 24 matrix. So you can actually write this UVW interpolation as H matrix into vector of elemental degrees of freedom DE. H is this and DE is this. So I have already said this is 3 by 24 and this is 24 by 1. So this is one, the interpolation for UVW, because we have that in the potential of body forces and surface tractions. So we need to include that. And then you have to also look at the strains. So the strains are, no, if you look at the strains, so let me write in the new page. So this is a strain. If you look at the strain, we had 6 non-zero components in, because 3D. So 3D means you will have all the 6 non-zero strains. Normal strain along x, y, and z, and the shear strains gamma xy, gamma yz. I'm writing yz first and then gamma zx. This is the sequence no I'm writing over here. So this will be in between you are going to have this interpolation matrix, the strain displacement matrix basically, and then the vector of elemental degrees of freedom. So if you look at the vector of elemental degrees of freedom, they are same. That is U1E, V1E, W1E, then U2E, V2E, W2E, and so on. And finally, we'll have U8E, V8E, and W8E. So these are the vector of elemental degrees of freedom. Now, if you recall, epsilon xx was del u by del x. So we need to differentiate u with respect to u, u with respect to x. So we have u is coming at first location, fourth location, and so on. So since it's a derivative with respect to x, so we will have to write the derivatives of the same functions with respect to x, of course, and then we will have no del n1 by del x 0 0, so that we get no del n1 by del x into u1e plus del n2 by del x into u2e, and so on. So that will give you basically the epsilon xx, which is del u by del x. So then you have del n2 by del x 0 0, del n3 by del x 0 0, and like that no, you will continue, and at the end you will have del n8 by del x 0 0. So this is epsilon xx. Epsilon y will be derivative of v with respect to y. So now when you look at the v is coming at second, fifth, and so on these locations, and derivatives with respect to y. So we'll put 0 here, and then we will have del n1 by del y. Now the derivative is with respect to y. 0 0 del n2 by del y, 0 0, del n3 by del y 0, and then you will have 0 del n8 by del y and 0. So this is epsilon yy. Epsilon zz is del w by del z. So it comes with the w degrees of freedom, which is third, sixth, and ninth, and so on. So 0 0, we'll have del n1 by del z. Now the derivatives of the shape function with respect to z now. 0 0 and del n2 by del z, 0 0 del n3 by del z, so on, and then be 0 0 del n8 by del z. So this is epsilon zz. Then gamma xy, is del u by del y plus del v by del x. So u and v both are coming. The derivative of u is with respect to y, and derivative of v is with respect to x. So in the u locations we will have del n1 by del y, and in the v locations we will have del n1 by del x. And then 0, w is not coming in that, and then del n2 by del y, del n2 by del x, 0, del n3 by del y, del n3 by del x, 0, and then we will have del n8 by del y, del n8 by del x, and 0. So this is gamma xy, and then you will have gamma yz. Gamma yz, now if you remember, it is gamma yz we have defined as del v by del z and del w by del y. So that means v and w are involved. The derivative of v with respect to z and the derivative of w is with respect to y. So u is not there, so we put 0, and v derivative is with respect to z, so we will put here del n1 by del z in the v location, and w is there, its derivative is with respect to y, so we will put del n1 by del y. Then 0 del n2 by del z and del n2 by del y, and then again 0 del n3 by del z, del n3 by del y, 0, and so on. And then same thing you will have here, 0 del n8 by del y and del n8 by del z. So, sorry, I wrote no, z and y. Here it is. This is no, because v derivatives with respect to z and w derivatives with respect to y. So we will have these as the interpolations for the gamma yz. And then if you look at gamma zx, so gamma zx is defined as del u by del z plus del w by del x. So basically u and w are involved. U derivative is with respect to z and w derivative is with respect to x. So we will have del n1 by del z, 0, and del n1 by del x, w derivative with respect to x. And then again we will have del n1 del n2 by del z, 0, and del n2 by del x, and then again del n3 by del z, 0, del n3 by del x. So this is the last strain, and similarly del n8 by del z, 0, and del n8 by del x. So this is what is going to be your strain displacement matrix. So you will see again the vector of elemental degrees of freedom is 24 by 1, and there are 6 strains and 24 degrees of freedom. So this is 6 by 24 matrix. So as per the standard notation, no, we call that as this matrix involving derivatives of shape functions as B, and this as DE. So this is your B and this is your D, and V is now 6 by 24 matrix and 24 by 1. So you will also realize that we cannot obviously solve the problems of using this 3D element manually, because the this B itself is 6 by 24, and when we do B transpose C into B, so we'll have to multiply those matrices, and the stiffness matrix is going to be upsized 24 by 24. So it's a very involved work, so it can only be done through a software or through the soft program written in Fortran C, etc. So either the commercial packages you can use for solving the real life problems or any problem, or you can use the you can develop codes in MATLAB, Fortran, C, C++, and then you can do these calculations. So that is how it would be done. Yeah, so now once we have defined the strain displacement matrix, the interpolation matrix for UVW, and all the six components of strain, then of course the development of the element level governing equations is straightforward. But before that, I haven't talked about. So I have already talked about the shape functions. So n1 to n8 are basically shape functions written in terms of natural coordinates xi, eta, and zeta. So now what we want to do is we need the derivatives of the shape functions with respect to physical coordinates x, y, and z. So for that you need to again write a Jacobian matrix the way we have done earlier. So if you look at the Jacobian matrix, so the concept is similar to what we did for the 2D problems, no two-dimensional functions of x and y. So similarly, you will have a Jacobian matrix. We already have x, y, and z expressed in terms of xi, eta, and zeta. So the Jacobian matrix is similar to del x by del xi, del y by del xi, and now we also have z here. So del z by del xi, and then we have del x by del eta, del y by del eta, and del z by del eta, and then we have del x by del zeta, del y by del zeta, and del z by del zeta. So this is your Jacobian matrix. And the Jacob, so now when you want to write the derivatives with respect to xyz in terms of derivatives with respect to xi, eta, and zeta, so you write this operator relationship. So the operator relationship is del by del x, del by del y, and del by del z. This operator relationship is J inverse. Now we take the inverse of the Jacobian matrix and multiply it with the derivative operators with respect to xi, eta, and zeta. The shape functions are already expressed in terms of xi, eta, and zeta. So if we say that no, the J inverse, you get actually this matrix, Jacobian matrix, and invert it. It's a transformation matrix. So let us say the J inverse is also going to be a 3 by 3 matrix. And let us say the elements of the inverse matrix are J11 star, J12 star, J13 star, and then the second row is J21 star, J22 star, J23 star, and J31 star, J32 star, and J33 star. So that is J inverse, and these operators remain del by del xi, del by del eta, and del by del zeta. So now if you want to write as you can see from this, if I want to write down the derivative of any shape function ni, so I can write del ni by del x, the derivative of a ith shape function with respect to x. So that would be basically J11 star into del ni by del xi plus J12 star into del ni by del eta plus J13 star into del ni by del zeta. So because the shape functions are already expressed in terms of xi, eta, and zeta, so these derivatives we can get explicitly, and then through this relationship then we can get the derivatives of all the shape functions with respect to x. So similarly, del ni by del y would be equal to J21 star del ni by del xi plus J22 star del ni by del eta and plus J23 star del ni by del zeta. And similarly, the derivatives of the shape functions with respect to z coordinate would be written as J31 star del ni by del xi plus J32 star del ni by del eta and plus J33 star del ni by del zeta. So now once you have, so everything is defined now. So at any given xi eta point, so you can calculate the basically you can express x, y, z in terms of xi and eta, then get the Jacobian matrix, get its inverse, and then know you can define the shape function derivatives with respect to xi, eta, and zeta, and then get their derivatives with respect to x, y, and z. So here basically in all these three, I goes from 1, 2, and so on up to 8. So this is for all the shape functions. So now the element level governing equation is the procedure is exactly the same. That is, you substitute the the interpolation for UVW and the interpolation for the strain in the total potential energy functional I, and then delta I equal to 0 gives you the element level governing equations. So if you look at for this case, the element level governing equation. So the element level governing equation is going to be, so the element level governing equation is going to be the same form, that is element level stiffness matrix Ke into De is equal to F external, which is due to the body forces, and the F internal, which is due to forces on the boundary of the element. So that we are in general calling it as a internal force, because in general there would be element around that particular element. So those elements, the will be boundary elements would be exerting the forces on this particular element. So we will have these internal forces. Now if you look at the Ke, so now here if we look at where now this Ke is basically now it would involve, so Ke comes from this term in the potential energy, that is this particular term. So epsilon you are going to write as B into D. So epsilon transpose would become D transpose B transpose C, and then epsilon is B into D. So D will take out. So then it's a volume integral. So volume integral dV means dx, dy, dz, and that integral is written in terms of natural coordinates. So the integration is from -1 to +1. So this integration is -1 to +1, -1 to +1. So it would involve triple integral, and then you will have, of course, from the first strain we get a B transpose, and then the constitutive matrix C, which is 6 by 6, and then again into B, and then the volume integral is written in terms of determinant of the Jacobian matrix into d high d eta d zeta. So this is the stiffness matrix. And no, as you see, this is B transpose is B is no, if you look at it, is 6 by 24, and C is a 6 by 6 matrix. B transpose would be 24 by 6. So ultimately the stiffness matrix is going to be a matrix of size 24 by 24, 24 rows and columns. So now of course the evaluation of the stiffness matrix is done through Gauss quadrature numerical integration. So earlier we have seen the two-dimensional integration. Now the triple integral would be replaced by a triple summation. So we will have summation, say I going from 1 to m, summation j going from 1 to n, and say summation k going from 1 to p. So then we evaluate this at each Gauss point. So that means we will have B transpose into C into B into determinant of the Jacobian matrix evaluated at xi I, eta j, and zeta k. So now we will have three coordinates at each Gauss point. Of course, those points are going to be same. So now we will have, of course, the then weight functions wi, wj, and wk. So this is how you will numerically evaluate this stiffness matrix. So I will talk about how to choose the number of points. So similarly, if you look at the F external, no, that is due to body forces. So that is also involving volume integral. So it would be a triple integral, and in the natural coordinate space, the integration would be from -1 to +1 in with respect to all the three coordinates. So you see the shape of the element can be anything in the physical coordinate space, but since it is mapped to a cube in the natural coordinate space, so these integrations are always from -1 to +1. So the limits are constant, -1 to +1 for all the three variables. So you have H transpose and the body force components FBX, FBY and FBZ. So these are three body forces and determinant of J into d high, d eta, d zeta. And this integral is also evaluated numerically. So again now triple summation. So that triple summation is, we have say I going from 1 to m dash, j going from 1 to n dash, and k going from 1 to p dash. So we have now here this H matrix. So you see this, of course here also the load vector, if you look at, this is a 3 by 1 vector, and H itself is a 3 by 24. Its transpose would be 24 by 3. So ultimately this external load vector would be finally 24 by 1. So we have H transpose into the components of the body forces FBX, FBY and FBZ, and then you have determinant of Jacobian matrix. This whole thing is evaluated at xi I, eta z and zeta k. And then you have wi, wj and wk, three weight factors. Now there are three weight factors which are coming over here. And if you now look at the third matrix, the vector, the internal force. So F internal is of course is involving now the surface integral. So that is integration over the surface, and we have basically H transpose and then the surface forces Tnx, Tny and Tnz, and into ds. Ds is a surface. Of course this has to be converted appropriately in terms of xi, eta, no eta, zeta, or xi and zeta. So depending on which surface we are in, when we are looking at all the six surfaces of the element. So element will have six surfaces. So that means this integration will span over summation over six surfaces when you are doing this. Now the choice of gas points, choice of number of gas points. So gas, in the gas quadrature numerical integration which we have written over here. So this choice of numerical number of gas points, how do we choose? So now if suppose let us say that the element is let's say a cuboid, not necessarily a cube but cuboid. So that means the edges are perpendicular to each other, but the side length could be different. So that is known as cuboid. And cube means the edges are perpendicular to each other and all the edges are of same length. So then you call it as a cube. And if the edges are not at right angles, so then we call that as a parallelopipe. So let us say that element is a cuboid in the physical coordinate space. In that case, you would see that the Jacobian matrix would be constant. We'll have only diagonal elements similar to 2D problems. So J would be constant. And now B is in terms of derivative of shape function with respect to x, y, and z. And they are in terms of derivatives of shape function with respect to xi, eta, and zeta, as we have seen. So since the highest power of xi, eta, and zeta in the shape functions which we discussed in the last class is going to be 1. Highest power of xi or eta or zeta in the shape functions is going to be 1. So when we take their derivatives, so one natural coordinate would go, but the highest power of other natural coordinates would still remain as 1. So if we take the power of in general, power of xi, eta, or zeta in B, so it would be 1, and again multiplied by B will be 1 plus 1, 2. So the highest power of xi, eta, or zeta is going to be basically 2. So if you look at the n, m, and p, this would be equal to highest power in the integrand. The quantity which we are integrating is 2 plus 1 divided by 2. So this is approximated to next integer. So that means we will take the values of n, m, and p as 2. So 2 points along the xi direction, 2 points along the eta directions, and 2 points along the zeta direction. So therefore you will have total integration would be 2 by 2 by 2. So that means there would be total 8 integration. So this means no, the integration is 2 by 2 by 2. That means total 8 gas points. Total 8 gas points are going to be there. So if you look at the element in the natural coordinate space, so if you look at this element in the natural coordinate space, that is in xi eta, so this side is eta, this side is xi coordinate, this is xi coordinate, and this side you have no from here xi eta, and this is zeta coordinate. So the points, if you look at, we will have 8 points, 2 points along the xi direction, 2 points along the eta direction, and 2 points along the zeta direction. So you will see that somewhere we will have those points are going to be somewhere here. They will not be just zeta equal to -1, but above that. So these points somewhere here, and similarly, somewhere here we will have these 4 points like this. So these will be the 8 integration points, 4 plus 4. So these are the integration points. So they are going to be combinations of 2 values of xi, 2 values of eta, and 2 values of zeta. So the coordinate values are going to be same. So if you remember, we have said for the 2 by 2 by 2 integration. See, the zeta 1 is going to be -1 upon root 3, and zeta 2 is going to be +1 upon root 3, and w1 is going to be w2 equal to 1. And similarly, if you look at the eta 1 would be -1 upon root 3, eta 2 would be equal to +1 upon root 3, and w's are same. So similarly, if you look at zeta 1 equal to -1 upon root 3, and zeta 2 equal to +1 upon root 3. So therefore, if you look at the 8 integration points, so the 8 integration points are going to be, if you look at the integration points. So what do you mean by integration point? That means you evaluate the Jacobian matrix, the derivatives of the shape functions with respect to xi eta at each these gas points, and then calculate the B matrix, multiply B transpose C, and the Jacobian determinant of the Jacobian matrix, and then multiply by the weight functions, weight factors, and then keep on adding. So integration points, if you look at in all, those 8 points are see, one point is going to be -1 upon root 3, -1 upon root 3, -1 upon root 3. That is xi eta zeta all are negative, and so that would be actually this point. Then you come to this point, so will be +1 upon root 3, -1 upon root 3, and then you have -1 upon root 3. That is the second point, this particular point. Then you go to now go to eta side. So the third point, let us say, is this point. So that is going to be again the third point is minus. So like that, you can write the combination. So zeta is -1 upon root 3, eta is +1 upon root 3, and zeta is -1 upon root 3. That is the third gas point. Fourth gas point would be actually this point, which is zeta is +1 upon root 3, eta is +1 upon root 3, and zeta is -1 upon root 3. So these are the first 4 gas points. So first this point, then this point, then this point, then this point. And then similarly, if you look at the top points, so same way you can write xi and eta values are going to be this. So fifth point would be this. Only thing is zeta would be positive, and the sixth point would be xi and eta these values, and zeta would be positive. Then the seventh would be xi and eta these values, and zeta would be positive. And the eighth point would be these values of xi and eta, and zeta would be positive. So like that, you can write the other points also. So this is how, so in the softwares, if you see, sometimes it is written that the integration is 2 by 2 by 2, And for some problems where the incompressibility is involved, so then you might have to do the reduced integration. And in case of reduced integration, instead of using 2 by 2 by 2 integration, you would use 1 by 1 by 1. So in case of 1 by 1, that means only one point along zeta and zeta directions, so that would be a single point. So see, two integration points in each direction leads to 8 integration points. And but if you are using one integration point in each direction, so there would be only one integration point over the entire element. That means you have to only once evaluate b determinant of j and the multiply and get the stiffness matrix. So this is about, of course, nm and p. But what about this n dash, m dash, and m dash, n dash, and p dash? So although you would see that only h is involved, so we could use highest power of zeta, and zeta is actually 1. So you could use 1 point, but most of the time what we do, we end up doing the same integration point. So m dash is equal to n dash is equal to p dash. We take actually 2, although it can be taken as 1, I just said, but we take the same whatever we use for the stiffness matrix. So this is how basically this formulation of the three-dimensional finite element is done. And no so you should understand that in each element, what are the assumptions made, what are the degrees of freedom, and how overall the how the element is done. So now, before I move on to, so the last element which is of interest to solving naval structural problems like ships and submarines, is the plate bending element. But before I move on to the plate bending element, let me, in 2D, I have only talked about so only the basically 4 noded element in 2D and 8 noded element in 3D. But we can go for higher degree polynomials. So then we will have 8 and 9 noded elements in basically 2D, and then you can have 20 or 27 noded element in 3D. So that is also possible. So only change is in the sizes of the matrices and the shape functions. But the development of the element level governing equation, assembly, imposition of boundary condition, and solution remains basically same. So I will just tell you that how to write the shape functions for a 2D 8-noded isoparametric element, and then I'll move on to the plate bending elements. So now 2D 8-noded, and why we are discussing so many elements, because these are the
Excuse me,
elements
sir.
we use. Yeah, yes, please.
Sir, can we
Yes.
solve an example related to 8 noded elements, sir?
No, we cannot do manually. That either you have to write a MATLAB code, or you have to use a software. Because you see there is a matrix size of 24 by 24. So do you think manually it is possible to solve? It is not possible. Of course, no heat conduction problem. If you take only 1 degree of freedom at each node, so then still the matrix size is going to be 8 by 8. So for that it could be done, but yeah, that is also quite involved. So it is not possible to solve the manually these the problems using these elements. You have to really use a package, or you have to develop a code in MATLAB, Fortran, C, etc., and then you can solve problems. So 2D 8 noded, I know the solution, although the steps are exactly the same. What we have done for 1D and 2D problems, whatever examples I have taken, so entire solution steps are exactly the same. So now I am discussing 2D isoparametric element. So I just want to only talk about the shape functions, because other things the are same. So the element what we have when you look at it in the physical coordinate space. Now I'm talking about 2D. So the unknown variables are only functions of 3 coordinates. So the element can have arbitrary shape with the edges even could be curved, so that you can model the problems with the curved boundaries. And the nodes are you have corner nodes. So these are the corner nodes, and then you have these mid side nodes. The element edges can be actually curved. The corner nodes are the local node numbers are 1, 2, 3, 4, 5, 6, 7, and 8. So this is the element in the physical coordinate space. This is mapped to an element in the natural coordinate space, which is a square. So then you have basically xi and eta, and the nodes are the 8 nodes again. So there is one-to-one correspondence between nodes 1, 2, 3, 4, 5, 6, 7, and 8 in the natural coordinate space. And if you look at the coordinates of these, so this is -1, -1, this coordinate is 0 and -1, this is 1 and -1. So this is 1 and -1, this coordinate, and then the coordinates of this point are -1 and 0. The coordinates of this node 6 are in the natural coordinate space, +1 and 0. And similarly, now you can write the coordinates. So node 3 is 1 and 1, and this node is 0 and 1. This node is -1 and 1. So these are the xi eta coordinates of each node. So you see, if we are solving a temperature problem, then we will assume an approximate solution for temperature. If we are solving for the plane stress, plane strain, or axisymmetric problems, then we will assume an approximate solution for UV and W. So suppose if I take the variable U, so U would be taken as a, now because there are at each node we are having primary variables, that is U, V and W as degrees of freedom. So U would be written as a 8-term polynomial. So earlier for the 4 noded element we had written 4-term approximate solution. So now U would be taken as U A0 plus A1 chi plus A2 eta plus A3 xi eta plus A4 xi square plus A5 eta square plus A6 xi square eta plus A7 xi eta square. So now what you would do is you would express these 8 constants A0, A1 up to A7 in terms of the values of U at node 1, 2, 3, 4, 5, 6, 7, and 8, and then you will ultimately write this in terms of the interpolation functions, and you would do that for all the variables. So that means ultimately you would write U equal to I going from 1 to 8 ni uie. V will be written as summation I going from 1 to 8. So now we are talking of 8 noded isoparametric element. So we'll have ni vie, and no, there are 2 displacements and 2 coordinates. So x is I going from 1 to 8 ni xi, and similarly we'll have y going I going from 1 to 8 ni yi. So this would be the interpolation, and no, you can only thing what changes is the interpolation function. So let me write the interpolation function. So what I am going to do is I am going to define all the set functions and explain you how to write these directly. Although no, there is a, you can get the 8 equations and solve for A0 up to A7 in terms of values of U at node points, and then substitute them back over here, collect the coefficients of different degrees of freedom, you get the set functions, but they can be written directly. So how do we write that directly? So now if you look at this element in the natural coordinate space, so this is xi and this is eta, and these are the way nodes we have already said 1, 2, 3, 4, 5, 6, 7, and 8. So now if you look at the equations of the line, so when I am writing n1, so I will have to know, except n1 I have to cover all the nodes. So nodes 2, 6, and 3 can be covered using this line, whose equation is 1 minus xi equal to 0. So I take that line 1 minus xi. Node 3, 7, and 4 can be covered using the equation of this line, which is eta equal to 1 or 1 minus eta equal to 0. So I take that equation, and then node 8 and 5 have to be covered. So for that we take, we have to take the minimum number of lines. So we take this line, and the equation of this line would be xi plus eta equal to -1 or 1 plus xi plus eta equal to 0. So we take that equation 1 plus xi plus eta, and then we'll have to make sure that this node is no, this say function n1 is unity at node 1. So the coordinates of node 1 are -1 and -1. So we put here this 1 minus minus 1 becomes 2 into 2, 4. And then here we'll get 1 minus 1 minus 1, so -1. So the value would be -4. So to make it unity at node 1, we need to divide it by -4. So we will have -1 upon 4. So this is n1. So when we write n1 like this, so you would see that n1 is unity at node 1 and 0 at all other nodes. So n1 would be 0 at node 2, 3, 4, 5, 6 and 7 and 8. So it is unity at 1, 0 at 2, 3, 4, 5, 6, 7 and 8. So similarly when you write n2, n2 is the shape function corresponding to this node. So now again I have to cover all other nodes, remaining nodes. So for that I take the equation of this line, which is basically 1 plus xi, because equation of this line is xi equal to -1 or 1 plus xi equal to 0. So I take that, and the equation of this line is still 1 minus eta. And the equation of now I have to cover no nodes 5 and 6, because I have covered all the nodes on this line, all the nodes on this line. So these two nodes are left out, so I'll have to take the equation of this line. The equation of this line is going to be basically 1 minus xi plus eta equal to 0. So I take that 1 minus xi plus eta. This equation again we have to make sure that this shape function is unity at node number 2. So node number 2, the coordinates are xi equal to +1 and eta equal to -1. So if you put here, you will actually get xi equal to +1, eta equal to -1. So 2 plus 2 into 2, you get 4. And then eta is -1, so you get minus. So you have -1/4 here. So with this, n2 is unity at node 2, 0 at node 1, 5, 6, 3, 7, 4 and 8. So like that, you can write all the shape functions. So similarly, n3 would be, when you look at this, so now I take the equation of this line and equation of this line, and then I have to cover basically the node 7 and 6. So if you look at the equation of this line is going to be basically the equation of this line, if you look at, would be 1 minus xi minus eta equal to 0. So n3 therefore would be 1 plus xi, 1 plus eta, and 1 minus xi minus eta whole multiplied by -1/4. And then n4 is corresponding to node number 4. So for that you take the equation of this line, equation of this line, and then you have to take the equation of this line. So you will find now the way the logic I gave, it would be n4 would be -1/4, 1 minus xi, 1 plus eta, and 1 plus xi minus eta. So these are n1, n2, n3, and 4. The n5, you keep in mind that this is different from 8-noded 3D element. An 8-noded 3D element is a element in 3-dimensional space. Now we are talking about the element in 2-dimensional space, where there are, for the plane stress, plane strain, and axisymmetric problem, there are two unknown displacements u and v, but there are 8 nodes, and all these things are functions of only two coordinates, xi and eta, and the physical coordinate functions of only x and y. So this difference you should keep in mind. Now when I want to write the shape function for node 5, so I have to take the equation of basically this line, equation of this line, and equation of this line. So this first line is basically 1 plus xi, because xi equal to -1, so you can say 1 plus xi equal to 0. And the right side line is xi equal to 1 or 1 minus xi equal to 0, so we take 1 minus xi. And this line, the third line is this line, which is eta equal to 1, or you can say 1 minus eta equal to 0, so 1 minus eta. And then we have to make sure that this shape function is unity at node number 5. The coordinates of node number 5 are 0 and -1. So if I put xi equal to 0 and eta equal to -1, I will get actually 2. So I have to divide it by 2. Now with this, n5 would be unity at node number 5 and would be 0 at all other nodes, 2, 6, 3, 7, 4, 8 and 1. It would be 0 at all those nodes. Of course, you can also write this as 1 by 2, 1 minus xi square into 1 minus eta, because 1 plus xi into 1 minus xi would be 1 minus xi square. So same way n6 when you are writing, so you will take the equation of this line, equation of this line, and the equation of this line. So you will have 1 plus xi is the equation of the left side line, and then the bottom is 1 plus eta, top is 1 minus eta, and then this has to be unity at node number 6. The coordinates of node 6 are 1 and 0, so we put here xi as 1 and eta as 0, we get 2, so we divide it by 1 by 2. So this can be written as 1 by 2, 1 plus xi into 1 minus eta square. Similarly, n7, the seventh shape function would be for this node. So we need to take the equations of these lines and this line, bottom line. So that will also know, you can look at the same logic. So n7 would be basically 1 plus xi, 1 minus xi, and 1 plus eta. So you can see that this is half 1 minus xi square into 1 plus eta. And so the eighth shape function would be then same way 1 by 2 for the node, this node. So for that you have to write the shape function, I know the equation of top line, bottom line, and the right side line. The right side line is 1 minus xi, the bottom one is 1 plus eta, top one is 1 minus eta. And so this ensures that n8 is unity at node 8 and 0 at all other nodes. That doesn't mean that it is 0 throughout the element, but it is 0 at those nodes. And this can be written as, of course, half and 1 minus xi, 1 minus eta square. So these are the 8 shape functions, and using of course you need to look at the derivatives of these shape functions with respect to xi and eta, and then through the Jacobian matrix you have to get their derivatives with respect to x and y, and then you will basically develop the element level governing equations. So I just want to give you a homework problem. So that is not developed. So the procedure is same. Develop element label governing equations for we have discussed three types of 2D structural elements. So plane stress and strain can be dealt together. So that is one. Plane stress, plane strain, and axisymmetric. So you basically have to write all the steps: axisymmetric, 8-noded, isoparametric, finite elements. So that is one. So there are others, smaller problems also I want to give. So this is one homework problem. The second homework problem is, suppose you have problem number 2 is, suppose you have the element in the physical coordinate space. So this is say x coordinate and this is a y axis. This is x, and the nodes are this element is bit arbitrary. So one node is here, one node is here, and the other side is, this is here. So this is the element in the physical coordinate space. This is node 1, this is node 2, this is node 3, 3 is here, and this is node 4. The coordinates, if you look at the coordinates of these nodes, so node 2 is at say 0 comma minus a, and node 3 is at a comma 0, node 4 is 0 comma a, and node 1, the coordinates of node 1, x and y coordinates of node 1 are a by 2 comma 0. So this is the element in the physical coordinate space, and this element is mapped to the square in the natural coordinate space. We have xi and eta, and these are the nodes 1 2 3 4. So you already now know the shape functions for these. So xi and eta is given. So now the xi eta are basically the natural coordinates. So what you have to do is you have to find the determinant of the Jacobian matrix for this. So find determinant j, that is determinant of the Jacobian matrix at 3 points. At point number 1 is xi equal to minus 1 upon root 3. These are actually Gauss points. Eta equal to minus 1 upon root 3. Point number 2. So actually, we expect this the area ratios have to be positive, but you see the element is too much distorted from the rectangular shape in the physical coordinate space, so then this determinant j may come out to be negative, and which is undesirable. So therefore, no, when you do the meshing, you have to make sure that the elements are of proper shape and size. So they should be close to square, and basically that is the ideal thing. But then there are some allowable limits. So the interior angles can vary from 45 degrees to basically say 225 degrees. That's about the angles, and the side ratios can be, the ratios could be 1 to 8. So that's the maximum distortion which is allowed. If the element shapes are distorted more than that, then your finite element results are not going to be accurate. So purpose of this is to just get an idea that the Jacobian matrix can become negative, which is undesirable. That would give erroneous results. So just calculate the Jacobian matrix at these points. So xi is second point is xi is minus 1 upon root 3 and eta is plus 1 upon root 3, and the third Gauss point is both xi and eta are plus 1 upon root 3. So you just do the calculation for this. The third problem I want to give you is the actually you should get an idea that how to do this. Not exactly the numerical calculation in this case. So if you have an element which is arbitrary quadrilateral in the physical coordinate space, so that means we actually structures we are modeling basically in the physical coordinate space. So these are the coordinates, and let's say it's a thermal problem. So the temperature values at these nodes are T1, T2, T3 and T4, and let us say these are given to you. If you know these values and the coordinates, so x1, y1, x2, y2, x3, y3, and then x4, y4. So these values are given, and of course this element is mapped to a square in the natural coordinate space. So that is xi and eta, and these are the four nodes 1, 2, 3 and 4. So now if no you have you should look at how to solve this kind of problem. So suppose you are given xi yi, that is all the x and y coordinates of all the nodes are given, the degrees of freedom are given, say the temperature in this case for I going from 1, 2, 3 and 4. So these all values are given, and also now we have some point P. The coordinates at that point are say xp and yp. So we are also given now this coordinates xp and yp, and there would be that point would be some corresponding point in the natural coordinate space, that is point P with the xi coordinates as xi p and eta p. So how will you solve? So xi, yi, ti are given, that is all the xy coordinates of all the nodes. So the temperature values or the displacement values are given for all the nodes. You are also given the physical coordinate of point inside the element xp and yp. So xp and yp are also given. So then you have to find the unknown variable, say t at point P. So now in this interpolation, the reason is because t is expressed in terms of xi and eta, whereas the point given is in the physical coordinate space xp and yp. So first we will have to find out xi p and eta p, and then evaluate the shape functions n1, n2, n3, n4 at that point, and then get the t value at that point. So how you will do is, now you know that xp will be equal to summation I going from 1 to 4 ni xi, and yp, y coordinate of point p would be I going from 1 to 4 ni yi. So from these two equations, xp is known, yp is known, and the x1, x2, x3, y1, y2, y3, y4 are known. So you have this side known xi and eta, this side no xi and eta. So there are two unknowns xi and eta, two equations. So you can solve for xi p and eta p. So from these two equations you will find xi p and eta p corresponding to this point. And once you know the xi p and eta p, then you can evaluate the shape function at this point, and then write t equal to summation I going from 1 to 4, Ni at point P, that is at xi P, eta P into Ti. So this is how we will do the calculation. So this is more like, understanding the steps. So the really the problems are 1 and 2. The third is to understand the steps. So yeah, so with this, now the next element I want to take. So I think fluid mechanics problems I am not actually discussing. So I think the similar way we could extend, the develop the elements for the fluid mechanics problems, and we can talk about fluid mechanics problems. But I think I'm not discussing that uh, because, if you're using any CFD package, so probably you would have done some fluid mechanics course, you would have some idea about that. So the next is I'm going to know one of the most important element for naval applications is the plate bending elements. So that is the next element I am actually going to discuss. And we are discussing mainly the formulation. I will not be able to take no numerical examples. That is manually is not possible because the sizes of the matrices are big. So the idea is that you understand the formulation so that you would be able to, if required, you can develop your own code or you can use the software packages, so you know what assumptions are made in the element, what is the formulation in the element, and so that you can properly use the element and interpret the results. So that is basically the idea. Although the steps, as far as the solution, all the steps are concerned, they are exactly similar to what we did in 1D and 2D problems. So evaluation of the element level stiffness matrix, assembly, imposition of boundary condition, solution, all those steps are exactly the same, only thing they are more involved. So that is why we are not, no, it is not possible to do over here. So next is I am now going to talk about plate bending element. So if you see the ship and submarine structure, so most of them are no, if the thickness of the the plates which will be there will be very less compared to the in-plane dimensions or dimensions between stiffeners. So they can be modeled as plate, and I think probably you will also be doing course on application of theory of plates and cells. So this is what we are. So there, of course, if you see, if you would have done the solutions, you would have seen that those analytical solutions are possible only for certain set of boundary conditions. But in real life, no, when you look at the complex structure, submarine structure, they are quite complex. The boundary conditions are not like those simply supported or clamp boundary condition, but they are more complex boundary conditions. And they are not no one single domain, but there are plates with multiple stiffeners along two directions, stringers and rings and so on. So no, you need a method which can model all kinds of problems. So that is why we use the plate bending elements. No, so we cannot solve all the plate bending problems using analytical solutions, and that is why we resort to finite element. And finite element is for a simple problem or a complex problem, it goes in the same manner. So that is why it's popular in all the design. When you do any structural design, you basically ultimately do through the finite element analysis, so using packages. So that is why we are discussing these elements. So next is plate bending elements. That is, I think I will discuss only one element. So I could discuss the classical plate bending element and first order shear deformation theory theory based plate elements, but I will discuss only one based on the first order shear deformation theory based plate bending element. That's what I'm going to discuss. So when you say plate, what do we mean by plate? So what we are saying, when can we model a structure using plate elements is, of course, if you look at the 3D solid element I discussed, 8 noded brick element, 3D solid element, that can be used for solving all problems. But then if one of the dimension is very small, so then in the other directions also the element edge length has to be almost of the, maybe it could be 7 8 times of the thickness, but that leads to a large number of elements. So that is why we resort to use or we resort to using 1D or 2D elements for the problems for the one dimension, at least it's much smaller compared to the other two dimensions. So when you say plate, so basically what we are saying that two in plane dimensions, so like A and B you might have studied, so two in plane dimensions, are significantly smaller compared to thickness of the plate compared to thickness. An additional thing is that loading is in the thickness direction, and loading, so maybe pressure loading or any other distributed loading. So loading, or maybe let's say if you have aircraft carrier, so when the aircraft is moving on the runway in the on the carrier, so there also you are going to have these plates, and there are line forces, or you can say concentrated forces, but they are in the thickness direction. So loading is in the thickness direction. So thickness direction, of course, we also refer to as transverse direction. So transverse.
Excuse me, sir.
Yeah.
Is it smaller or it should be larger compared to
Yes,
thickness?
please. Your voice is not clear.
Sir, is it
Can you?
smaller or it should be larger in compared to thickness, sir?
The implant. Yeah, no, significantly larger. I'm sorry. Yeah. Thanks for correcting this. Yeah, they are larger, not smaller. Yes. They are significantly larger. Yeah, thanks for correcting this. So two in-plane dimensions are significantly larger compared to thickness, and loading is in the thickness or the transverse direction. So if we have this situation, then we basically model that structure as a plate element. So now if you again, if you look at the so far what we did, if you look at the element library so far we discussed, so far, no, we have discussed 1D elements. So where one dimension is significantly larger compared to the cross-sectional dimensions. So that is no, like we talked about truss and beam and frame elements. So here one dimension is significantly larger along the length compared to the cross-sectional dimensions. So then we can model that using either truss, beam or frame elements depending on the kind of loading. So we have discussed truss, beam and frame element. Of course, beam and frame we have discussed only in 2D. You could have a beam or frame oriented in 3D, and so you have to include the bending in other plane and torsion also in that case. But that's where we have limited, and of course it can be extended. And then in the 2D elements, if you look at as far as the structures are concerned, so then two dimensions are significantly larger compared to the third dimensions. But in the 2D elements, so far we discussed the loading is in the in-plane direction. So the difference between the plane stress, plane strain and problems is with the plate problem is that in plane stress, plane strain problems, the loading is in the in the plane of significant dimensions. Whereas in the case of plate, the loading is in the transverse direction. So we discussed, of course, the plane stress, plane strain, and axisymmetric. Axisymmetric, of course, sometimes in the packages is classified under 3D solid elements, but no, I prefer to put under 2D. So this is what we have discussed. And then we have also discussed the 3D element, which can always be used for any problem. But only thing is, no, the discretization has to be fine enough. So the number of elements would be very large. So 8 noded brick elements. So these are the elements which we have discussed, and these elements are no used, when you use any package or any for any analysis or design work of structural design work, you will use these elements, one of these elements or maybe combination of these elements. Sometimes you use more than one type of element for solving a particular problem. So you might use plate bending element, some portions you might use solid elements, some portions you might use the frame element. So that kind of a situation would be there. So now next we are under 2D elements, we are discussing another plate bending element where no, there is a loading in the transverse direction. So two in-plane dimensions are larger compared to thickness, but the loading is in the transverse direction. So now if you look at plate bending, so I think let me sketch a simple plate of what we are talking about over here. So you have no, this is plate, so this is the x and y coordinate directions, and this is z. I'm sketching a right hand triad, and I'm just saying that no, the length and the width of the plate are a and b. So compare to no the thickness h. So if h is the thickness, compared to h, a and b are large, or h is smaller compared to a and b, and the loading is in case of plane stress, plane strain, the loading was along x and y. So whether it is the body forces or the boundary forces, they are all along x and y. Now in the plate case, plate bending case, the loads which are there, they are in the transverse direction. So let us say there is a force in the transverse direction, that is q. So this is the problem we are talking about. So now if you look at there can be also, because when you talk of complex structures like ship and submarine structures, so all the plates are not in the same plane, they are actually in different plane. So transverse loading in one plane will lead to in plane loading and no partially in plane and partially bending in the other plane. So then you also ultimately end up having the in plane as well as the transverse load. So under that, if you look at the displacement field for plate bending element, so no, it is similar to when I look at the displacement, I will have three displacements which are functions of x, y, and z. So u along x, v along y, and w along z. So these are three displacement u, v, w. But what is the difference from the 3D element is that in this case, we basically take the known variation of all the three displacements along the third, the thickness direction, that is z direction. So, based on the different plate theories, one of them is classical plate theory, which I am not discussing. Probably you would have done in application of theory of plates and cells, how the displacements UV, are approximated in classical plate theory using along the x, y, and z directions. But I am going to do, because that's the most common finite element used in the softwares. So that is why I am discussing the element which is based on first order shear deformation theory. So now in this, if you look at what we are now going to do, we are going to approximate the displacements along the thickness direction. So in the first order, in the classical plate theory, the transverse shear stresses are neglected. So we assume that the plane sections normal to the plane middle surface remain normal after deformation. But that assumption is relaxed in the first order shear deformation theory. So that means classical plate theory is applicable for only very thin plates. So maybe like A by H ratio is greater than, let's say 20 or so, so 20, 100 and so on. But if A by H ratio, that is in plane dimension to thickness ratio, is less than 20, say 10, 5, then you have to use the shear deformation theory. So that is what I am discussing here. So in the first order shear deformation theory, what you do, the displacement along x direction, which is a function of x, y, z, is written as the displacement of a point on the mid surface. So u naught xy. So this is somewhat similar to, if you remember, we have done the frame element using Timosenko beam theory. So it is somewhat similar. So we had in plane displacement, and then we have z, and into here we will have rotation about y axis. So theta y. So u naught is a function of x, theta y is a known function of x and y. But no u, this u is a known function of z, that is a linear function of z. So how we are writing this? So in this plate, if I take any xz plane, so for example, if you take this xz plane, so in the undeformed configuration, this is my xz plane, any arbitrary xz plane, and so this is x and this is z, and of course the y coordinate is like this. And when I take the rotation about positive y axis, so let us say after deformation, this element goes somewhere here. And then if I take a normal over here, this normal, so this normal goes somewhere here, this normal takes this shape. And if I take the center line, so this is the center line. So essentially I am saying that this normal has moved from this position to now this position. And so that means if you look at, there is a displacement of the central point. So if I take point at z equal to 0, This is also point at z equal to 0. So that has got displaced by an amount u naught. Then additionally, if I take a point at a distance z, no this point, no this distance is, let us say, z. So this angle, if you look at this angle is the rotation about y axis, so that is theta y, and then this the additional displacement at this point. So this length is going to be z into theta y. So that is how I am writing the displacement of this point as u naught plus z into theta y. So that is the displacement u. So we are assuming u to be linear function of z. Then if you look at displacement along y direction, so v, which is a function of x, y and z, so that is written as v naught, which is a function of x and y. So u naught and v naught are the displacement along x and y direction of any point on the middle surface of the plate, that is z equal to 0, midway in the thickness. And then we consider the rotation about x axis, so minus z into theta x, which is a function of x and y. How I'm writing that is, to actually write this, you take any plane, basically yz plane, that is this kind of a plane, any yz plane. So if you take yz plane, so this is yz plane, this is y coordinate, this is z coordinate. As per the right hand triad, no x would be coming in this direction. So if I take the rotation about x axis as positive, so this has theta x. So you would see that this element is going to be, so if I take any element here, this normal here, and this is z equal to 0 point, and this is a point at a distance z. So this will ultimately deform and this normal will move somewhere there. So the center point, this point has moved by a distance of basically v naught, that's the center point. And then this rotation, if you look at that, rotation is theta x. So this distance, if you look at this distance is going to be z into theta x, but it is in the negative y direction. If you look at this displacement, so let me show in a larger view. So what I'm showing over there is that this is the normal after deformation. This is a line parallel to vertical line, initial, that is line parallel to initial z axis. Let me put somewhere so that it goes through the center. So basically, this angle is theta x. This is a rotation about positive x axis. And then if I take a point at a distance z, so this distance is, that is what I'm talking about, z into theta x. But you see, compared to this point is moving along the negative y direction. So that is why there is a minus z into theta x over here. So you will keep in mind that here theta x is the rotation about x axis and theta y is the rotation about y axis. In the literature you will also see that u is written as u naught plus z into theta x and v is written as v naught plus z into theta y. So then actually the theta x there is the rotation about positive y axis and theta y is the rotation about negative x axis. So that difference you should keep in mind. But in the packages, when you look at the degrees of freedom, so they are there as basically displacements along x, y, z directions, and that is u naught, v naught and w, and then you have rotations about x and y, theta x, theta y, and of course for the assembly regions we also have the rotation about z axis, theta z. So this is uv approximation, and then w of course is assumed to be only function of x and y. So I think so let me just define what are u naught, v naught and theta x, theta y and w, and then I'll stop and continue in the next class. So here you see I have used this u naught, v naught, which are functions of x, y. So these are basically, I have explained them through the diagrams, but let me also write. So displacements of points on middle surface, that is z equal to 0. Points on middle surface means z equal to 0 along x and y. Displacements of points on middle surface, z equal to 0 along x and y. So that means u naught is the displacement of any point on the middle surface of the plate along x. V naught is the displacement of any point on the middle surface, z equal to 0 along y. And theta x here, keep in mind, very important, this is rotation about x-axis. So rotation of the normal about x-axis, and theta y is rotation about y-axis. And w, of course, is the transverse displacement along z direction. Transverse displacement along z direction. And the main the main assumption here is, like in classical plate theory, you assume that normal to the middle surface, straight normal to the middle surface, remain straight and normal after deformation. That's the main assumption in classical plate theory. Here the assumption is that we still keep that assumption that straight normal remains straight but need not be normal to the middle surface after deformation. So here main assumption is, so if you look at in this, the main assumption is that straight normal to middle surface. Middle surface means z equal to 0, surface mid of the thickness. So straight normal to middle surface remains straight after deformation. So we are taking note that this line here, as I said, this line, no, this straight normal remains a straight line. It doesn't get curved. If it gets curved, then no, this approximation of u and v along z would not be just function linear in z, but it will have quadratic and cubic terms and so on. So that's the main assumption we are making, that straight normal to middle surface remains straight after deformation, but not necessarily in a specific situation. It could be, but not necessarily normal. So basically in classical plate theory, you assume that it remains straight and normal. Here we are assuming that it remains straight but not necessarily normal. So I think this is where I want to stop. And if you want to ask couple of questions, some questions you can ask. We will continue, of course, in the next class about the rest of the development of this plate bending element. So yeah, if you have any questions